Hi Algebra students, we are on the final day of our enrichment activities, so let's go ahead and take a look at the last couple of pages here. Quadratic formula, hopefully we have this one memorized, we've done this one recently. Make sure your functions are always in standard form first. So for our first two examples, that requires us to either subtract 15 from both sides or subtract 3x squared from both sides. There are other options. I chose to move one term. I could have moved two terms to the left here. Either way, we have to get it equal to 0 first. Then remember, we want to find b squared minus 4ac first. That's going to give us a lot of information, plus just make the calculation a lot easier. So for number 19, both a and b, when we find b squared minus 4ac, in this case we get 676, that becomes the radicand, so that's some new vocab, that goes under the square root, and we take the opposite of b plus or minus, so that's two problems. When we add, we get 3 over 4, when we subtract, we get negative 2 over 5, after we divide by 2 times a. Same idea here, but b squared minus 4ac gives us 148, that goes inside the square root. Perform two different operations, and we had to round our answers in this case. Here we did 0.75 or 3/4, negative 2/5. If you wanted to put that as an improper fraction, perfectly acceptable as well. For number 20, this was just how many solutions. In this case, when we're asking how many, all we care about is b squared minus 4ac. It doesn't change the fact that we need these in standard form first. So part B, we would have to first put in standard form, write it as x squared plus 6x, subtract 14 from both sides, minus 14 equals 0. So when we check b squared minus 4ac, and again remember this is the part that's going underneath the square root, in part A we get a negative number, negative 211. The 211 part doesn't matter. The negative part is what does. Can't have a negative inside your square root, can't do that. So we have no solution here. And in part B we get 92. The 92 also doesn't matter as much when we're answering how many. The fact that it's positive is what matters. When you take that square root now, when you do plus or minus, that will give you two solutions. The only way to get one solution is if our number for b squared minus 4ac is equal to exactly 0. Then when you add 0, you're going to get the same thing as when you subtract 0, so you're only going to have one solution. And in part 2 for chapter 9, we are talking about the graphs of our quadratic functions. First, putting our quadratic functions in order from narrowest to widest. Remember, what we are looking for here is the value of a. A is the coefficient of our x squared term. Ax squared plus bx plus c. The a is what's giving us this information. If it's positive, it opens up. If it's negative, it opens down. But when we're asking specifically about narrowest to widest, we're asking how close it is to 0. So we're looking at absolute values. The farther that number is away from 0, the more we're stretching this vertically, and that means the more narrow it becomes. The closer it is to 0, then we're compressing it, we're pushing it way down, and so it's getting really, really wide. So when we have a 3, a 1/3, and a negative 5 is the furthest number away from 0. That's going to be the narrowest. Y equals negative 5x squared. Because the 5 is furthest from 0, the next furthest from 0 is 3, so 3x squared would be the next narrowest, and then y equals 1/3 x squared is going to be the widest, because that is going to be the closest number in this group to 0. When we are moving our quadratic graphs, our parabolas up and down, that has to do with your y-intercept, that has to do with your constant. This is when we're focused on, we have ax squared plus bx plus c. C is what's telling us when we're moving things and translating them up and down. In this case, this is a little bit complex, but these, if we put these in standard form, we would have plus 16 as my constant, plus 16 as my constant. Here my constant is 0. This is the only one that's plus 4. This is our translation up 4 units. Axis of symmetry, this is where we know x is equal to the opposite of b all divided by 2a. Axis of symmetry is always the equation of a vertical line. So for part A, the opposite of b divided by 2a, x is equal to -1. For part B, x is equal to -2/3. Alright, to finish off number 23, the vertex for part A is going to be -1, -3. We take the x-coordinate for the axis of symmetry, plug that back into our function for x, and solve for y, gives us our y-coordinate. For part B, same concept. Our x value at the axis of symmetry substituted into our original function for x, solve, we get y is 1, there's our vertex. And then again, if the domain is what we're looking for and there's no context to the problem, all real numbers. Our x values are the domain, so all real numbers are our double R bar, I think is what we were calling it. Alright, the last thing that we talked about after we took our Chapter 9 test, and then we quizzed on this right before we were done, the linear versus quadratic versus exponential functions. This is where we're looking at differences, and then we're looking for common ratios. For something to be linear, we have to have a common first difference in our y values. Quadratic is a common second difference in our y values. And for exponential, it's a common ratio. So we take a look at specifically our y values, and we're looking for those items. And we can look at our first differences, we can look at our x value differences as well. Those are also important. But if the first differences aren't there, look at the second difference in y. If the second differences aren't there, look at the common ratio. For the first example, first differences were not constant, second differences were not constant, so I checked my ratios. And the common ratio here is multiplying by 1/2 or dividing by 2. Either way, it's a common ratio. That makes this an exponential function. For the second one, change in y is constant the first time. So it's a first difference is constant. That makes this a linear function. And on the third one, first differences were not constant, second differences were, so I don't have to check for common ratios. That makes this a quadratic. Solving the following system. I know we did a lot of this using substitution, so we have that y is equal to x squared minus 5x minus 4, and y is equal to -2x. So we can take the y that's equal to x squared minus 5x minus 4 and substitute that in to the y here, giving us x squared minus 5x minus 4 is equal to -2x. From here, make it equal to 0 and solve using any of our methods that we've worked on. So when we get this equal to 0, we could solve by factoring or the zero product property without going through all the details of factoring that you did on a previous video. X minus 4 times x plus 1 is 0. Zero product property says one of those factors has to be 0, so x is 4 or -1. The other option we've used a lot is quadratic formula. And if we use quadratic formula, we get the same thing. B squared minus 4ac is 25. 3 plus or minus 5 divided by 2 is going to give us either 4 or -1. The last idea is sketching graph of a system of linear and quadratic equations that meet these criteria. So again, recognizing that when they want it to be a system of linear and quadratic, if it's linear, I have to graph a line, and then if it's a quadratic, I have to graph a parabola. So for two solutions, whatever my parabola looks like, either opens up or down, it's narrow or wide. No solutions, and I'll just change things up. I'll draw one that opens down and is narrow, and then one solution, I'll draw one that looks a little bit closer to a parent function. those are my parabolas. The lines for two solutions, I will have two intersections. That gives me one solution here and one solution here, both as ordered pairs. When we have no solutions, that means the line and the parabola will never intersect. And when there is one solution, that wasn't a perfect one there, but we can imagine that I did that perfectly, and those just barely touched right down here near the vertex in this case. Alright folks, so that's our review of what we've done thus far this semester. Hopefully things have gone well. Feel free to contact your teachers with extra questions. Good luck, and hope everybody is doing well and staying safe.